Good afternoon, everyone. Good afternoon, Antriksh. How are you? So today we are here for another lecture on magnetic effect of current. Very good, Antriksh. मैं बढ़िया हूँ एकदम. Okay. So let's start. First thing that we are going to start in the previous class, what we have completed is the magnetic force on a moving charge, and we have taken some questions over there. Now we will start with some Lorentz force. What is Lorentz force? So if I say in one word or one statement, what is this Lorentz force? So let's suppose a charge. There is a charge which is moving with some velocity. And this charge is moving in the presence of some electric field and magnetic field as well. That means in a region when there are both kind of fields, electric field and magnetic field, both are present in the region. So let's suppose this is the direction of electric field E and this is the direction of magnetic field B. So in this situation, there will be both the forces acting on the particle or acting on the charge. So the net force on the particle is the vector sum of electric force and the magnetic force. Am I clear to you? What I was saying that when a charge moves in an electric field and magnetic field, both are present simultaneously, then the charge will experience both the forces, and this combination of forces is known as Lorentz force. Out of which this one is known as Lorentz electric force and this one is known as Lorentz magnetic force. Depending on this phenomena, what you can conclude that a charge can experience electric and magnetic force both at the same time. So depending on this phenomena, there are various devices which were formed. Like one of the famous devices which used these two fields is velocity selector. So let's go to that velocity selector device, which is very important. So we are moving towards velocity selector. What is a velocity selector? I will describe you in few minutes. So first thing is velocity selector, as the name suggests, it is a device which is used, like, first of all, listen to me. What I was saying, like you have seen in chemistry classes, like alpha particles were bombarded on the gold foil, like gold foil experiment you have studied, I hope, in the chapter atoms and nuclei or whatever, that alpha particles were bombarded with some velocity. So the particles which are bombarded on a particular object or target must have same velocity for the experiment point of view. So this same velocity is provided by the velocity selector. So what I was saying, it is a device which is used or it is used to pass or to filter the particles of velocity which is other than the selected velocity. For example, you want the particles of 100 meter per second to reach the target, and you don't want the particles moving with lesser velocity or higher velocity to reach the target. So this device will filter out the particles which are moving faster or slower than the desired velocity, which is in this case is 100 meter per second as we have selected. So this is the device. Now, what is the setup looks like? For example, I'm telling you the setup of the device. These were the two plates. These were the two plates. Let's suppose this plate is positively charged and the bottom plate is negatively charged. These are the plates. And after that, there is a uniform magnetic field in this region, which is into the plane. This is uniform magnetic field. Let's suppose this field is B. And due to these plates, positive and negative plates, one electric field will also create. And this electric field will be in the downward direction from positive to negative, like this way. This is the direction of electric field, you will say. Clear? Now, let's suppose this is a charge Q moving with some velocity V and it enters the region. Now, the situation is something, there is a target. Let's suppose this is the target at which I want that this charge particle will strike. So, this is the target. Now, listen to me. This charge particle will hit the target only if it is going in a straight line. Only if it is going in a straight line, it will hit the target. So this is the path that it should follow. Because if it deviates from its straight line path, then it will not strike the target. So this is the condition. Now, if you look at the charge particle at any of the point, let's suppose at this point I am considering the charge particle is present. Now tell me just one thing. What will be the direction of electric force on this particle and what will be the magnitude? What will be the direction of electric force or electrostatic force acting on this particle when it is at this point Q? At this point that is marked as yellow. What will be the direction of electrostatic force? Can anyone answer? Am I audible? Okay, I'm explaining it again. Okay, I am audible, right? Okay. So my question is, I'm explaining the question. There is the situation is like there is a electric field in the downward direction. This electric field is marked with the arrow E. And there is a magnetic field in the into the plane that is inward direction. Now the charge is moving horizontally. What I am saying that charge will reach the target only if it follows the straight line path. So the my question at this point is what is the direction of force acting on this charge Q at this point? At this point, what will be the direction of electrostatic force acting on this particle? Like this particle is moving in this direction, velocity is this, and electric field is in the downward direction. So you have studied that electrostatic force is equals to Q into E. I hope you remember this. Electrostatic force is what? Q into E. And this electrostatic force acts in the direction of electric field. So the force is Q into E acting in downward direction. Till now, everything is clear. This is electrostatic force. Now, one more thing. Can you see that there is a magnetic field as well? So it will experience some magnetic force as well. So what will be the direction of magnetic force? What will be the direction of magnetic force? Can you use the right hand rule to find the direction of magnetic force? I will say magnetic force is what? Q. Formula I have written V cross B. This is the formula. And for direction, what you should do? Q V cross B. That means you should take your right hand, put the velocity, put the fingers in the direction of velocity, and put your palm in the direction of magnetic field, and you will find that magnetic force is in the upward direction. So magnetic force will be Q V B. Angle between velocity and field is 90, so I am not mentioning sine 90 as one. This will act in the upward direction. So at any point, at any location inside the plates, charge will face two forces. One is in the downward direction, one is in the upward direction, but the path it should follow must be a straight line. So the for path to be a straight line, the net force on it must be zero. Are you getting my point? Why the net force must be zero? Let's suppose if net force is not zero and electrostatic force is larger than the magnetic force, so charge will move in the downward direction. And if magnetic force is more, charge will move in the upward direction. So that's why I am saying that both these forces must be equal and opposite. So condition here, what I am saying for particle to reach the target, very good. To reach the target, these forces must be equal. That means magnetic force must be equal to the electrostatic force. As we have seen, that direction is already opposite, so we don't need to deal with this. So magnitude, if I equate, that means QVB is equals to QE. And if you can cancel Q, velocity of the particle is equals to E over B. This is the golden relation that you should remember. V is equals to E divided by B, E over B. This is the velocity. The particles moving with this velocity will reach the target, and particle moving with any other velocity, whether it's greater than V or less than V, they will not reach the target. They will not reach the target. Now just answer one thing. First of all, try to remember this relation. Next is, let's suppose if velocity is greater than this V, what will happen? I am saying that if the particle which is entering this particle has more velocity than this much of velocity, what will happen? You can clearly see that if you increase the velocity, the force, magnetic force will increase. Just listen to my words very carefully. This magnetic force will increase. Can you see that if you increase this velocity, the magnetic force will increase? And if magnetic force will increase, you can see that equilibrium will be disturbed because electrostatic force remains constant. So magnetic force will increase, and you can say that particle will move in the upward direction, and it will not follow the straight line path. It will move in the upward direction like this, and it will not reach the target. So it is deviated from the path. Are you getting my point? And if velocity, so what is the conclusion? If velocity is greater than V, it will move towards positive plate. Now, can you answer one more question here? What if velocity is less than the velocity V? V is what? V is this much of velocity. Then what will happen? It will move downward. Very good. Clear? Okay. So on this note, this is the velocity selector that we have to study. Moving further, checkpoint. Okay. So there is a question actually that I will ask, and you need to answer the question. Question is very simple. Let's suppose a particle is moving in a circular path. The question is not written over here, so I am just trying to put some data here. A particle is moving in a circular path in the presence of a magnetic field. In the presence of a magnetic field, let's suppose magnetic field is B, which is into the plane, which is into the plane, and particle is revolving in this circular path like this. and the particle which is revolving has some charge q and some mass m. Clear? Q is the mass of the particle, q is the charge, m is the mass of the particle, magnetic field is B. And just listen to one more point. When the particle reaches the topmost point, when it was at this topmost point, suddenly an electric field is turned on. What I'm saying, try to listen and try to note down the question. What I'm saying, when charge is at highest point, electric field E is switched on. Clear? Now, the particle follows the straight line path, or particle starts moving along the tangent from this point, and particle is moving like this. Initially, it was revolving in a circular path. Now, as soon as the electric field is switched on, it started moving along the tangent from that point. So, what is your task? Your task is to calculate, find E, find E, and the radius of the circular path is R. This is given. Radius of the circular path is R. First of all, tell me whether question is clear to you. Particle was initially moving in a circular path of radius R. It has some charge Q. Okay, I'm repeating. Particle was initially moving in a circular path in the presence of a magnetic field B. Clear? Now, the charge of the particle is Q, mass is M, radius is R. Now, suddenly, one electric field E is turned on, and it is seen that particle starts moving along the tangent from the highest point. It was at the highest point, and the particle starts moving along the tangent. So, what will be the magnitude of this electric field? What will be the magnitude of this electric field? This is the question. And you should answer one more thing. What should be the direction of electric field which is turned on? What should be the direction of electric field which is turned on? So without wasting any time, just tell me the direction of electric field. After that, we will move further for the next part, the magnitude of electric field. Just try to figure out the direction of electric field. Upward. Okay. So upward is the answer given by Antriksh. Let's consider the situation. The magnetic force on this particle will act in the downward direction. That's for sure. You can see that magnetic force is acting in the downward direction. Now, for particle to move along the straight line, the electrostatic force must be in the upward direction. Are you getting my point? Now, listen to me. These are the basic concept of, I will say, Newton's laws of motion thing. The magnetic force is in the downward direction. How? Okay, that's what you are asking. Why? Okay. Use your right hand thumb rule. This is the direction of velocity. You can say this is velocity at this point. Use your right hand. V cross B, thumb will be in the downward direction. So this is the magnetic force. Now, for particle to move in the straight line, that means the net force should be zero. So the another force must be in the upward direction. So another force is in the upward direction. That means electric field is in the upward direction. The one thing is clear, electric field is in the upward direction. Now, what I'm saying, net magnetic force should be equals to electrostatic force. Again, you can say QVB is equals to QE. Q and Q can be cancelled. So electric field is equals to V into B. Now velocity is what? When particle is moving in a circular path. When particle is moving in a circular path, everybody knows that its radius is given as R is equals to mv over qb. So velocity can be written as R qb over m. Put this velocity here. So electric field will be R qb by m into b. That is R qb square by m. This is the electric field. And in which direction? In upward direction. Is it clear? I hope the question is clear. What you should do, this is again the principle that we have used in the velocity selector is implemented in the question. Is this point clear? After that, we will move further towards the another device. How V comes by R. Okay. This is the formula for the radius. Do you remember this relation? R is equals to mv by qb. When a particle moves in a magnetic field, its radius is given by mv by qb. Now, velocity is, I have transferred the q and b from the denominator to the numerator, rqb by m. I have transferred, solved it for velocity. Now, I have put the velocity in this equation. Let's suppose this is equation number 1. I have put the velocity and I got the answer. This is what I did here. Clear? Moving further. Cyclotron. You're welcome. Cyclotron. This is another device that I will say, which is very important to understand what's happening here. First of all, what is cyclotron? It is a device which is generally used to accelerate the charged particles. The theoretical description you will understand in your classes when you will get the classes in your respective JNVs. Now I am just telling you the basic points, the conceptual points that you should know. One thing that is to be very clear, it is used to accelerate the charged particle. Like suppose you have a charged particle and you want to provide it certain velocity. So how will you provide it a certain velocity? By using the device cyclotron. What is the construction of this cyclotron device? The construction is very simple. One is it has, first of all, if I can draw for you the schematic diagram I am just trying to draw, it has some conducting hollow plates in the shape of D. I don't know whether I can draw it properly, but can you imagine that this is a sheet which is hollow from the inside and in the form of a D. And similar D is placed opposite to that, like this. Similar D is placed opposite to that. This is again a hollow. I hope you can imagine. These are the two identical D-shaped conducting materials which are hollow from the inside. Now, one thing is clear. Another thing is they have connected a very high frequency oscillator through these two Ds. These are conducting Ds and they have connected a high frequency oscillator. I will tell you the work of the high frequency oscillator later. Now, another thing, this is placed in the horizontal plane. These Ds are placed in the horizontal plane. Can you see my hand? I hope it is visible. It is placed in the horizontal plane. And above and below it, there are north and south pole to create a magnetic field. So there is a magnetic field going into this. There is a magnetic field going into these Ds. Now, what does this high frequency oscillator does? This high frequency oscillator gives these Ds some charges like positive and negative charges. And it just changes the polarity of these charges. It changes the polarity from positive to negative. Once initially, let's suppose D1 is positively charged and D2 is negatively charged. After some time, D2 will become positive and D1 will become negative. So this is the task of the high frequency oscillator, to provide the polarity to the Ds and to change its polarity. And high frequency means it performs these tasks very quickly. This is why high frequency. Now you can imagine that if this plate is positively charged, this plate is negatively charged, there will be an electric field like this. Clear? And due to these poles or magnetic poles, due to these magnetic poles, this is south pole, this is north pole, there is a magnetic field in the downward direction from north pole to south pole. So can you see that there is magnetic field and there is electric field? Both the fields are present. Now, what is the principle behind it? Let's suppose in the diagram, this plate is positively charged initially, and this is negatively charged. Try to figure out the things. This plate is positively charged, so what is the direction of electric field from positive to negative? Again, listen to me. Let's suppose a charge is introduced in the space between the two Ds. There is a charge. Can you see the marking that I am making? Can you see this? This is the charge which is introduced. Now, this charge is initially at rest. I have introduced this charge to accelerate, and this charge is initially at rest. But due to the electric field, which is in the right direction or in this direction, you can see that electric field is in this direction. This charge particle will start moving like this. It will start moving. Now, as soon as it start moving, it gains some velocity. And as soon as it enters the D, there is no electric field, because electric field inside the conductor is zero. Electric field inside the conductor is zero. That means there is only magnetic field acting, and this magnetic field will try to rotate it in a circular path, and the particle will start rotating or start moving in a circular path like this. And after completing the semicircle, it comes out of the D, and suddenly it finds that polarity of the D's gets changed. Now it become positive and second D become negative. Due to this, it again gets accelerated and enters another D, and this is why it start moving in a some kind of spiral path like this. And in between the D's, its velocity increases by the electric field. And inside the D, it is being rotated in the circular path. So what's happening? There are two fields. One is electric, one is magnetic. Now listen to me. What is the conclusion that I can infer here? There are two fields. What are the two fields? One is magnetic field, one is electric field. What is magnetic field doing? It is just rotating the particle, nothing else. What is electric field doing? It is accelerating the particle. It is accelerating the particle. So try to remember these two tasks. Magnetic field is rotating the particle, electric field is accelerating the particle. So someone may ask you, who is responsible for the increased rotating the particle in the circular path. Now, another question that comes to our mind, what will be the frequency of the cyclotron? So I have written something over here. For that, I hope I need to delete this. I will write it on the next slide. What you should remember, what should be the frequency of the cyclotron? Frequency of the cyclotron is nothing but QB divided by 2 pi m. What is Q? Charge of the particle. B is the magnetic field. M is the mass of the particle. Each and every term is very much clear. QB over 2 pi m. This is the frequency of the cyclotron. Now, one more thing that you should remember. For example, the particle is moving in this circular part or in this spiral path, then it will gain some velocity. Velocity keeps on increasing. Then what will be the maximum kinetic energy that it can have? So the maximum kinetic energy, the relation for the maximum kinetic energy that you should remember is this one: half r square q square b square by m. What is r here? Radius of d. What is D here? D is this shape, conducting shaped hollow conductor, or D shaped hollow conductor. R is the radius of this D. I hope this point is clear. Try to note down these two relations. On these two relations only you will find questions for the cyclotron. Nothing else, nothing more than that you will get in your exam. Now the line that I was talking about, B provides circular path to the particle and E accelerate those particles. These are the punchlines that you should remember. Now we are moving towards next concept. This is the most important concept. Okay. Now listen. This is very important thing to remember actually. Let's suppose there is a conductor. This is a current carrying conductor, or you can say current carrying wire. Whatever you want to call it, it is a current carrying wire. Let's suppose it has some current I. Clear? And its length is L. Its length is L. And this conductor is placed in the magnetic field B. Conductor is placed in the magnetic field B. So what will be the force acting on the conductor? There is a derivation for this part, but I am not going with the derivation part. You can learn that derivation in your classes. What I am saying, I am telling you the result. What is the result? So what I am saying, I am not solving it for the complete conductor of wire. I am just telling you for the small part of this wire. Let's suppose a small part is dl. So the force on this dl part, I will say force on dl is very small force. Df is equals to idl cross b. This is the magnetic force on a current carrying wire, or you can say magnetic force on a current element placed in uniform magnetic field. Now for the complete wire, you can integrate it, and if you integrate it, it will become df, it will integrate f is equals to il cross b. Now this is again a very simple thing to remember. I hope you have studied that well before in your classes. What is the magnetic force on a small current element is idl cross b. And for the complete straight wire of length L, I will say it will become, if you integrate it, it will become IL cross B. These are the very important, very fundamental formulas that you should remember. Now, coming to the point, which is very important. Now, the conclusion thing. First conclusion, the direction of this force. Again, you can clearly see that as we have taken 4, 5 classes already, you can see that the direction of force can be decided by the cross product dl cross b. So direction of force is same as the cross product or the vector product idl cross b. That means the direction of idl cross b will be same as the direction of magnetic force, or force will have the same direction as the idl cross b. So for that, you should know how to calculate the direction of vector product A cross B that we have already learned in the previous few classes. So I'm not going to tell, just use your right hand rule and you can find the direction. Now my question to you, for this diagram, tell me the direction of force. For this diagram, tell me the direction of force. Can anyone tell me? Use your right hand rule. Can anyone answer the direction of force? Say yes or no at least, so that I can explain if you are not getting the direction of force. Okay, I will tell you. First of all, listen, the statement is clear to you. Force is same, direction of force is same as the vector product IDL cross B. That means you should place your fingers, the fingers of your right hand in the direction of current I, or in the direction of current element IDL. So direction of I is in the upward direction. Place your right hand fingers in the upward direction like this. So am I visible? Yeah. Place your right hand fingers in the upward direction. Now put your palm in the second vector, in the direction of second vector, which is B. Put your palm in the second vector, which is inside, which is into the plane. You can see B is into the plane. So I have turned my palm into the plane. Now curl your fingers and thumb will indicate the direction of magnetic force. So thumb is going in the left direction from my frame of reference, or you can say the magnetic force will act in this direction. Is the concept clear to you? First, place your right hand fingers according to IDL, then put your palm in the direction of magnetic field and thumb will indicate the direction of force. So I will ask one question here to confirm whether it is clear to you or not. So I am asking one question. Let's suppose this is the wire which has some current I, and this is the magnetic field B. This magnetic field is coming out of the paper or out of the screen that you are watching. So tell me the direction of magnetic force. Tell me the direction of magnetic force. Students, you are joining very late. Antriksh is saying in the upward direction. Very good, Antriksh. Your answer is correct. It is in the upward direction. Magnetic force is going to be in the upward direction. Very good. Now, after knowing this, one point that I also want to clear here, that let's suppose this is the wire you have seen, and this wire has some force F. But at which point this force will act? So this force will act at the center of the wire. So what I will say, F will act at the midpoint of the wire. Clear? You should note down these things. Again, moving further. Now listen to me one more thing, which is very interesting. Let's suppose somewhat wire is some irregular shape. For example, it is not a straight wire. For example, wire is something like that. This is the shape of the wire, and it has some current I. Clear? And there is a magnetic field B. Now, what we should do? So, from this point, I will explain one very interesting point here, that magnetic force is nothing but I L effective cross B. Now, let me just explain what is L effective. After that, you can ask any question. What is L effective? L effective is the line joining the initial point of the wire to the last point of the wire. So this length is going to be L effective. This is L effective. What is L effective? I am repeating my words again. The line joining the initial point of the wire from where the current has started to the last point of the wire. So this line joining is known as L effective. Clear this point. So whenever you see some irregular shaped wire, then which formula you should follow? It is not always IL cross B, it is IL effective cross B. What is L effective? I have explained you in this slide. What is L effective? For example, if I tell you, let's suppose there is a semicircle and current is going this way and it has a radius R. What is L effective in this case? Can anyone tell me? What is L effective in this case? It's a simple question. What is L effective? Okay, I'm repeating my question. Should I repeat the question or should I repeat the concept here? Antriksh, concept. I'm repeating my concept. Whenever you see some irregular shaped wire and you want to calculate the magnetic force on that wire. So for that, what you should do, the formula that we have seen on the previous slide was IL cross B. This is for the straight wire. This is for the straight wire of length L. Now for irregular shaped wire, what is the actual formula? I L effective cross B. And what is L effective? The line joining the initial point to the final point is known as L effective. Line joining the initial point to the final point is known as L effective. This is same like the displacement that you have studied in class 11th. So in this particular question, I am asking, like suppose this is a semicircular wire of radius R, then what will be the effective length? What will be the L effective? In this question, what is L effective? My question is simple. Now tell me the answer. What is L effective? The line joining the initial point. Is this the initial point? And is this the final point? The line joining these 2 points is the L effective. This is L effective. What is this length? Can you see that this is radius, this is radius, so L effective is 2R. L effective is 2R. Are you getting my point? What is L effective? L effective is 2R in this case. Is this concept clear? Everyone. Okay, everyone should say yes or no at least so that I can take the attendance of the schools. How many schools are present there? Say at least yes, no, present, whatever you want, you can say before moving to the next slide. Okay, Antriksh says yes, sir. Everyone should reply at least anything. They can say present, sir, so that I can see how many students are there in the class. Okay. Yeli is present. Now, there are few punchlines. There are few punchlines. Remember this. Purvashri. Very good, Purvashri. Now, these punchlines are very important. Very, very important. What is the first punchline? Net magnetic force on a loop in a uniform magnetic field is zero. What is the what is this? What are they talking about? For example, let's suppose there is a circular loop. There is a circular loop and it has some current, let's suppose I, is present in a uniform magnetic field B. And they are asking you the magnetic force acting on this wire or on this loop. So what I have told you that magnetic force is IL effective cross B. That's what you have learned. Now, what is L effective? You can see that if current is starting from this point, after completing the loop, it is ending at the same point. Can you see that? That L effective in this case is zero. Can anyone see this? That L effective in this case is zero. And if L effective is zero, you can clearly see that this whole term will become zero. So the magnetic force on the loop is zero. So what is the statement? That whenever they are talking about uniform field, try to capture the words. Uniform field they are talking and they are talking about loop. The magnetic force is always going to be zero. Is this statement clear? Second statement is quite obvious. I will not explain this. Magnetic force is perpendicular to the magnetic field. This is very obvious statement. I don't need to tell you actually. Moving further. Now it's time to some questions. It's a very simple question. Tell me the answer. You have just 10 seconds. You have 10 seconds. Very quickly. Everyone, Yeli, Antariksh, and one more person was there who said yes, sir. I just forgot. Antariksh is saying A. Anyone else? Yeli, can you answer? Be quick in your responses. I can't see your names. So only the person who is commenting, I can only see the name of that person. So Yeli is saying option A. One more person was there. I'm waiting for her response or her or his response. I just forgot her name. Okay. Two persons have replied the same option, that is option number A. Now listen to me. Find the magnetic force on a semicircular loop as shown. This is the semicircular loop, and you have committed the same mistake that we have dealt in the previous part. What is the force? Cuckoo is saying option D. Very good, Cuckoo. F is I L effective cross B. Now try to understand the situation first. Can you see that L effective is what? From initial point to final point. Is this clear? So this is our L effective. The direction of L effective, can you see this one? This is our L effective. Say yes or no. Now, if this is our L effective and this is our magnetic field, which is also in the same direction, what is the angle between? If you open this, then it will become IL effective into B into sine theta. What is the angle between L effective and magnetic field? You can see that these two are parallel to each other. That means angle is zero. And if angle is zero, so it will become IL effective into B into sine zero. And sine zero is nothing but zero. So the whole term will become zero. Is this statement clear to you? Try to figure out the situation. Try to find out a way. It's not like I have asked the same question on the previous slide, so I must have changed something. So what I have changed something, I have changed the direction of magnetic field in this question. So try to be attentive in the class. I hope this is clear. एक बार जोर से बोल दो yes sir. We will focus on every parameter in the question. We will focus on direction of magnetic field. We will focus on direction of L effective. We will focus on L effective. Yes, sir. Very good, Antriksh. Now moving further for the next question. Now practice questions. These are some PYQs type of question. So now level of question has increased suddenly. I will just explain the question first. I'm not giving you time to solve this question because there are no options, so you cannot answer in terms of options. What it shows, figure shows two long metal rails. These are two long metal rails that you can see that with the highlighter pen. These are two long metal rails placed horizontally and parallel to each other at a separation L. That means the separation between them, this separation is L. Clear? A uniform magnetic field B exists in the vertically downward direction. This is the magnetic field which is indicated by cross symbols. A wire of mass M can slide on the rails. Very good. This is the wire that you can see. This is the wire. It can slide on the rails. The rails are connected to a constant current source which drives a current I in the circuit. You can see that there is a I current in the circuit and which is flowing in this direction. Okay. The friction coefficient between the rails and the wire is mu. What should be the minimum value of mu which can prevent the wire from sliding on the rails? So, someone, is the question clear to you? What they are trying to ask? After that, we will do the necessary calculation. But is the question clear to you? First of all, you can see that the current is moving in this direction, I. Is the color visible? Now, one thing. After looking at the diagram, can anyone tell me that what is the direction of, okay, leave it. Can you tell me the magnetic force will act on the wire or not? I'm just talking about the wire. And wire is, let's suppose this is PQ is the wire. Let's suppose PQ is the wire. Can anyone tell me, will there be any magnetic force acting on this wire or not? Just be quick, very quick. If yes, then in which direction? You can use your right hand thumb rule. Current is going in the, according to the diagram in this direction, put your fingers. Magnetic field is inward. So you can see that, very good, Kuku. Magnetic force will act and the direction of magnetic force will be something like that. This is the direction of magnetic force. Capital F, I have denoted it. Now, the wire will have a tendency to move in this direction. So the friction must act in the opposite direction. So friction must act in the opposite direction. And they are talking about the minimum value of mu which can prevent the wire from sliding. So can you conclude one thing? If wire is not sliding, that means the two forces must be equal and opposite. They are opposite, we can see. So their magnitude must be same. That means F should be equals to small f. What is F? Is I, L, B. It is given as length is given as small l, magnetic field is given as B, current is I. Is equals to what is friction? You know that friction is mu into mg. I hope you remember this. Friction is what? Mu mg. So what is mu here? Mu is what? ILB by mg. Very simple statement that mu must be ILB by mg. This is our first part which is solved, which is done. Now, just come to the second part. What are they saying? In the second part, they are saying describe the motion of the wire if the value of mu is half the value found in the previous part. Now, suppose mu dash is what? Half of the original value. Half of the original value is ILB by 2 mg. Is it clear? This is the new friction coefficient. Now they are asking what will be the motion. What will be the motion means you need to decide whether the wire will move, or if it will move, then what will be its acceleration. Now, again, I will say F, this force is acting in the right direction. Friction is acting in the left direction, should be equals to mass into acceleration. This is the equation of laws of motion. Second law of motion, net force is equals to mass into acceleration. Now, what is the magnetic force? You can ask at any point, what is magnetic force? ILB. What is friction? That is mu mg, or you can say mu dash mg is equals to ma. Put the values. ILB minus mu dash is what? ILB by 2 mg into mg is equals to ma. Mg and mg can be cancelled. At any point, you can ask if you have faced any doubt. So what's remaining? ILB minus ILB by 2. That means ILB by 2 is equals to ma. So what is acceleration? ILB by 2m. This is the acceleration of the particle. So when they are talking about describe the motion, that means you should describe whether particle will move. Yes, particle will move. In which direction it will move? It will move in the direction of horizontal force or magnetic force. And this force, this wire will move with this much of acceleration. Question was, however, tough. Not that tough, but easy. But you should understand the concept. Now, same question, same concept is applied on an inclined plane on the next slide, which you have to complete in your homework. These were the questions that were asked in the JE exams. So if you can come early in the class, you can ask me, sir, मुझसे homework नहीं हुआ. You can ask me so that I can explain the homework as well. So on this note, I am ending the session. Bye, everyone. Thank you. Thank you. Purvashri, thank you.